Assalamualaikum warahmatullahi wabarakatuh and very pleasant afternoon to ladies and gentlemen, members of the floor. My name is Muhammad Syazwan K190 and today I'm very honored and pleasure to present my research work entitled Artificial Neural Network Driven Optimization of Iron Oxide Nanoparticles PVDF Microspheres Phantom Light System for Methylene Blue Degradations. I'm representing MZUIT Nanoparticle College and Interface Industrial Research Laboratory, UITM, Changan Pulau Pinang. Ladies and gentlemen, the main grand challenge we're talking about the wastewater pollution nowadays is about industrial dyes. Example of the most commonly most polluted dye is the methylene blue, which is a major source of water pollution. However, conventional treatment methods have their own limitation in terms of the cost, efficiency, and also slash generation. Therefore, there's an urgent and pressing needs for a sustainable and efficient solution to meet the Sustainable Development Goals, especially SDG number 6, pertaining to the clean water and sanitation. Ladies and gentlemen, our solution in this work is introducing the phantom light reaction. So what is phantom light reaction? It's a powerful advanced oxidation process for dye degradation while using heterogeneous materials that enable to recycle and also avoid the slash generation from the pollutant removal. In this case, we utilize, and we employ iron oxide nanoparticles that have been encapsulated in a PVDF or polyvinylidene fluoride polymer microspheres, which is a novel, efficient, and reusable catalyst. In this work, ladies and gentlemen, we utilize artificial neural network (ANNN) as a cutting-edge tool for optimizing the complex process. Ladies and gentlemen, for the material methods, we synthesize the nanoparticles, iron oxide nanoparticles, using a typical co-precipitation method, whereby the PVDF microspheres were prepared by using typical phase inversion method. We employ methylene blue dye as the model dye pollutant in this case. We use the characterization of scanning electron microscope to visualize the top surface as well as the inner surface of this catalytic system. Measure experiments to evaluate the methylene blue decolorization under the varying conditions such as initial pH, catalyst loading, and hydrogen peroxide dosage. We employed a statistical experimental design to collect the data, and we developed the feed-forward backpropagation artificial neural network model for accurate prediction and optimization of the methylene blue decolorization. Ladies and gentlemen, based on our results in this work, our scanning electron microscope images reveal the smooth outer surface of the microspheres with a certain amount of porous structure on top of that. However, if we go into detail, the inner structure of the microspheres as compared in these particular SEM images reveal the complex interconnected porous interior structure, which really helpful in accommodating and immobilize the iron oxide nanoparticles on the surface, and the variation on pore size which enable from the range of micropore to the mesopore and also the macropore, so that it can assist the kinetics of the phantom light reaction. These properties enhance surface area and facilitate efficient diffusion of reactant, especially in this case is our methylene blue dye as a model pollutant. Ladies and gentlemen, moving on to the artificial neural network model element. After collecting the data, we use the feed-forward backpropagation artificial neural network models with the incorporation of the input layers of initial pH, catalyst loading, and hydrogen peroxide dosage. We developed the ANN model to predict accurately the methylene blue decolorization by varying the hidden layers of neurons into the true neurons with the output layer of methylene blue decolorization. We employ the Levenberg-Marquardt backpropagation model training algorithm and using the hyperbolic tangent sigmoid or tan sig transfer function. From here, we develop and varies the parameters of the artificial neural network in order for us to model the most accurate methylene blue decolorization. In the results, our ANN model performance demonstrated that the high predictive accuracy of coefficient of determination R squared of 0.9744 with a correlation coefficient of R by 0.9871, which is approaching 1, which is very accurate. In terms of the performance of the model indicators such as the mean square error demonstrated very low error in 0.02 as well as the root mean square error RMSE of 0.1414. What we can conclude here is the model effectively captures the complex dynamic of methylene blue decolorization, and using the algorithm, we managed to predict the methylene blue decolorization effectively. In conclusion, we successfully developed a novel ionocyte nanoparticles PVDF phantom-like system, macrospheres phantom-like system for efficient methylene blue degradation. We successfully optimized the process using an artificial neural network model and demonstrated the potential of integrating machine learning with chemical engineering for sustainable water treatment. This approach can be extended to other pollutants and processes. The future work, we would like to investigate the long-term stability and reusability of this model ionocyte and PVDF catalysts, explore the application of the system for the degradation of other industrial dyes and also pollutants such as emerging pollutants. And last but not least, we would like to develop more sophisticated artificial neural network models to further enhance the process optimization. As we know, there's a lot of opportunity for us to grow in this research area. Last but not least, we would like to acknowledge Ministry of Higher Education Malaysia via the FRJS grant for the support and financial support in order for us to complete this work. We also would like to acknowledge our Industrial Research Laboratory MZUITM Nanoparticle Colloids and Interface Industrial Research Laboratory or NanoCore, a collaborative work between UITM and MZ Holdings Sudan Berhad. With that, my name is Muhammad Syazwan K190. Thank you for listening. Bye.